Hello, welcome to this module. We're going to be covering maximum likelihood estimation. Starting off with a quote, this will kind of summarize what maximum likelihood estimation is about, but here we go. So the principle of maximum likelihood provides a method of estimating the parameters of a statistical model. Under general conditions, the maximum likelihood estimate is consistent, asymptotically normal, and efficient. So recall from our earlier section that we discussed the ideas of consistency, asymptotically normal. As the sample size increases, it should resemble a normal distribution, and efficient. And this was written by David Friedman. He's an American statistician. What we're going to be covering today. So MLE definition, some of it drawbacks, normal distribution, MLE, binomial distribution, and exponential distribution, MLE. And now I would like to point out that this maximum likelihood estimation is closely related to optimization, especially taking the logs, right? We saw in our earlier modules on calculus, like taking the log of a function, exponentials, like why these things are important, okay? And taking partial derivatives, right? So MLE definition, the maximum likelihood estimation is a method used in statistics to estimate the parameters of probability distribution based on observed data. The principle behind MLE is to find a set of parameter values that maximize the likelihood function, which represents the probability of observing the given data under a specific set of parameter values. So some clarification in terms of wording. One of the confusing aspects of MLE for some people is understanding the concepts of likelihood, right? So likelihood is used in probability, and this is not it. In MLE, the likelihood means basically how well the parameters of a statistical model explain the observed data, okay? So for example, like we'll given a data set, X is equal to X1 to Xn, right? The maximum likelihood function, L theta conditioned on X, which is the data, is defined as the probability of observing the given data X under the assumed statistical model parameterized by theta. The goal of maximum likelihood estimation is to find the value of theta that maximizes this likelihood function. The likelihood function L theta X is typically expressed as a joint probability density function or probability mass function of the observed data X, conditioned on the parameter theta. It's often denoted as the product of individual probabilities of observing each data point xi, right? This here is a multiplication symbol, so we're multiplying this f of x, I given theta, which is either going to be a probability density function or probability mass function, okay? It's not going to be a CDF, okay? So the PDF is important here. To find the maximum likelihood estimate of theta hat, we seek the value of theta that maximizes the likelihood function. Theta hat is equal to argmax L theta x, okay, with respect to theta. We saw this term argmax in programming, actually, and it does mean the same thing, okay, in this case, except it's applied to an actual statistical function, but it's a similar idea. So maximum likelihood drawback. So I'd like to have you, before you read this on your own, if you have or you haven't, after this lecture, if you decide to, please review modules 4 and 5, just in case you've forgotten some of the ideas. But let's continue. So additionally, MLE may encounter challenges such as finding the global maximum of the likelihood function, especially in high dimensional parameter spaces or when the likelihood function is non-convex. And we saw this earlier where there's multiple stationary points, multiple minimums, multiple maximums. And that's a difficult situation, right? When there's multiple local maxima and minima, right? It's difficult to find that minimum point that optimizes the estimate of the parameters, right? Moreover, MLE assumes that the data are independent and identically distributed, which may not always hold true in real-world scenarios, leading to potential biases in the estimation. We saw that in a multivariate normal where X and Y at one point were like moving together where they're correlated. So that would not be good. Independence basically means that one observation doesn't influence the other. Okay. And I mentioned like before, convex functions are ideal, right? I think by now you should probably know this, but this is way better than something like this, right? I would rather prefer some convex function like that. And so would the algorithms. So let's start off with a normal distribution MLE. Again, X is equal to X1 to Xn. It's IID, independent, identically distributed. According to a normal distribution with mean mu and standard deviation sigma, the likelihood function L mu given sigma given X is given by this. And here is the multiplication of multiple probability density functions for a normal distribution, okay? So to find the likelihood function MLE of mu and sigma, we maximize the likelihood function. Taking the logarithm of the likelihood function, we get the log likelihood. Okay, so this is a derivation of this. Now recall that we had this multiplication. If we could take the log, we could convert it into like some kind of additive property, which is this summation symbol here, right? We saw that in our earlier calculus section, which gave logs and some of the properties of logs. That's what it's basically doing here. Now, if we take the log of e to the negative x minus mu, it's just this term here, which we get here, right? And this is log of this term, which is negative 1/2 log 2 pi sigma squared, okay? The MLE estimates of mu hat and sigma hat are obtained by finding the values of mu and sigma that maximize the log likelihood function. Okay. Now, if we want to find the log likelihood with respect to the mean parameter, we would get this term here. Okay. And this function represents the logarithm of the likelihood of observing the given data X under the assumption that they're sampled from a normal distribution with mean mu and standard deviation sigma. And we just maximize this, okay? So we have this log likelihood mean. We calculate the log likelihood values for each mu value, right? Because we're basically iterating 1 to n, which could be 1, 2, 3, 4, right? Whatever it may be, right? Here. And we use the list comprehension. Recall from our Python class. And we find the argmax of the log likelihood values, right? Recall from this thing right here. Okay. And that's the ML mean. And we find this that it's maximized at negative 150. I mean, obviously negative 150 to negative 350, the scale, this was going to be the maximum. Okay. They do use a term like minimizing the negative log likelihood, right? So if we're going to minimize the negative log likelihood, that would also be saying negative 150. It's the same term as maximizing the log likelihood. That's what's basically used though, minimizing the negative log likelihood. That's the term that people tend to use in machine learning and whatnot. So I just want you to be familiar with that. And then we take the log likelihood function of the variance parameter. Okay. And we, derive this from that original function. And we do pretty much the same thing, okay? Recall location 2, 1. And we get a variance parameter of 1 here. And the mean parameter is, yeah, around 2. So like when we set this, these are like this is our actual population where the true population parameters, right? And then based on that observed data, we would get 1 for the variance and 2 for the mean. It's pretty close. I mean, it's pretty much the same thing. So those maximum likelihood estimation estimates are doing a good job of actually telling us what the data actually is, right? We could also use the minimize function here, minimizing the negative log likelihood, right? Which indirectly means you're maximizing the log likelihood. I know that's a little bit, it could be a little bit confusing at first when you hear it, but if you think about it a little bit clearer, it makes sense, right? And here we get this. Okay, so this is the MLE generated PDF, and it fits the synthetic data pretty well. People, I think you could go over this code and get like a better sense of what's happening. Okay, we're going to be using this minimize function later on in optimization as well. So getting a little bit of a grasp of like running it, seeing what it looks like, maybe playing with the different parameters, location, scale, seeing like how that works out is all experimentation and building intuition as to like what the MLE maximum likelihood estimation is actually doing. Now we go on to the binomial distribution MLE. Recall this is a discrete distribution. So given a data set x1 to xn, it's sampled from a binomial distribution with parameters n and p, right? And how do we obtain p? So we basically, remember, the original binomial function is multiplicative, it's multiplying. And by taking logs, we make it additive, right? And then we derive the log likelihood. We take the derivative with respect to p, and we get that term here, this term here. And then finally, when we do some algebraic rearranging of terms, we get this. So p hat is equal to x bar, which is just the sample mean. Now, if we try this, right, this is the probability of 6.5, and we generate about 1,000 binomial random variables. And then we calculate the MLE P, which is basically just this term here. We get MLE of 0.5, which is exactly the probability of success that was used to generate our distribution. So again, it does like a perfect job, okay? I also do a binomial, the log likelihood function for the binomial using SciPy. I don't evaluate the function though. I get the log likelihood here. So that's just to show you basically another way of doing things with the SciPy, but I don't evaluate the function. Moving on to exponential distribution MLE, the maximum likelihood estimation of exponential distribution. Again, the likelihood function is basically a multiplication of this lambda e to the lambda x, right? We're going to multiply this out n times, right? It's n to the n power e to the negative lambda summation x, okay? And then if we take the logs, right, we make it an additive relationship, so it reduces to this term here. And then we take the partial derivative, this is what we get. And then finally, we get this term. Now, if we run this, we get the MLE for lambda as 0.498 because we're taking the mean of the sample mean of the data. Okay. And I show it basically here, which is approximately 2 for this exponential distribution, which makes sense here from the original population parameter. So it works out. I do have some recommended reading for this whole statistics section in general. I've got a graduate school textbook, Haag and Craig, and yeah, I mean, I leave a PDF link here, and that basically wraps it up. Thank you very much, and have a good one.